Good day. Welcome to this video on multithreaded algorithms, a part of the series of videos on advanced algorithms. In this video, I will talk about multithreaded algorithms and I will show an example of how to parallelize an algorithm. But first, let's recap in a few words the multi-threaded programming model that we assume and the main concepts of analysis of algorithms in this model. So we assume what we call a dynamic multi-threaded programming model, where the main primitive is the ability to spawn a parallel thread. So I can write a spawn keyword in front of the function call, and this means that this function is executed in parallel to the any code that is here. And then there is a keyword sync, which means that we have here a synchronization point where I wait for both A and B to finish. Another primitive that we have is called parallel loops, where I put a parallel keyword in front of a for loop, and this means that I run the body of the loop, all the iterations of the loop in parallel. In different parallel programming models, this may be a important parallelization primitive, but in the model that we assume, this is just a syntactic shorthand for a divide and conquer algorithm using the spawn primitive, or what is called a nested parallelism, which means that I just divide my range in two, keep dividing my range in two until I get to a single iteration, and then I perform these iterations in parallel. But they have to perform work creating all these threads. So then that's how the execution tree would look like. I would, at the top, I would create two threads. These threads would create two threads each. I would spawn two threads each, and so on until I get to individual iterations. Each iteration is the base case of this recursive algorithm. To analyze these algorithms, we have two important concepts. One is called span, which is, putting it informally, just the worst case running time of the algorithm on a machine that has infinite number of threads. It can create infinite number of threads, so all things that can run in parallel actually run in parallel. That's the span. In the lecture we define it a little bit more formally, but this is a good way to think about it. The work is just the plain old worst case running time on a sequential computer. And then the parallelism is the work divided by span. And the goal of the algorithm design is to maximize parallelism so that the algorithm can use the parallel capabilities of the machine that runs it as much as possible. So returning to the analysis of these primitives, it's obvious that the span of this fragment of code is just the maximum of spans of A and B. Whichever finishes first, that dominates. And then the span of this kind of loop is the span of this divide and conquer algorithm, which has this divide phase where it keeps creating threads, so thread creation phase, and that has depth log n. So that's this log n, And then at the very bottom is the base case of all of this execution. It executes these iterations, the body of the loop. So then we have to add the maximum running time of any of these n iterations. So how do we parallelize an algorithm? Sort of one possible strategy is to first maybe try to see if some of the loops can be easily parallelized by just adding the parallel keyword in front of them. We cannot parallelize all the loops in this way, as we saw in the lecture. If one iteration of the loop depends on the other iteration, so A2 needs the results of A1, obviously we cannot perform them in parallel. We cannot access the same piece of memory if we want to update it in different iterations of the loop. We can get into something what is called race conditions. So not all loops can be parallelized. Then we want to maybe divide the algorithm, split the algorithm into stages, each of which can be converted into a divide and conquer algorithm. And so then we'll be able to call, to perform the recursive calls in parallel in this divide and conquer algorithm. That is actually the main strategy for creating parallel algorithms in this model. Make them divide and conquer. And if needed, maybe break the algorithm into stages so that each part can be made into a divide and conquer algorithm. So let's look at a simple example of how this works in practice. So the problem that we are going to look at is the same problem that we had in the previous video, namely the problem of removing duplicates from the array of n numbers. Array A, this is the input array, and we want to return the results in a different array, let's call it B, and we want the order of these numbers as they were in A to be preserved in B. So there are different ways of doing that, as I mentioned, but one of the simple ways of doing that is this nested loop implementation, where, again, this is exactly the same as it was in the previous video. You go through the whole array from 1 to n, and for each element you check if you can find it anywhere ahead of it, starting from I plus first position to n in the array. If yes, then it's not unique, it's false. And this means that if it's not unique, I do not include it. This version of the element, I do not include it in the output array. Otherwise, if it's unique, I add it to the output array. And I return the output array and the number of elements in it. So that is the algorithm. Obviously, the worst case running time of that is n squared. It's described by a simple arithmetic series. So how do we parallelize this? Know that so the first thing that we want to check, maybe we can write parallel keyword in front of these for loops and make it parallel in this way. We cannot do this for this loop because there is this global variable r that is incremented. So this would create race conditions if multiple threads would access the same variable, and it will not be clear in which order these elements will be added to the to array B. So we cannot, in this way, in this simple way, we cannot parallelize the outer loop. How about the inner loop? They also, all of the threads corresponding to all of the iterations of the inner loop would also access and update a global variable unique. Maybe on some specific implementation that would work, because if one of them set the value to false, we know that it's false. But let's assume we cannot do that. In general, we cannot update the global variable by several threads at the same time. So we also cannot simply write parallel in front of this loop. But what we can do is we can rewrite this into a parallel divide and conquer algorithm that would correspond to this loop. So let's do that. Let's try to see whether we can rewrite this as a divide and conquer procedure. So instead of saying unique equals true, I say unique equals the result of a call to the procedure check. For uniqueness, let's call it check u, which obviously gets this a as a parameter and I as a parameter. So in order to parallelize this part, we write a divide and conquer algorithm called check unique, which checks if this element at position I is anywhere in the range of the array starting from I plus 1 to n. So the algorithm should return true if this I cannot be found anywhere in the array starting from position I plus 1 up to position n. So here's the simple divide and conquer algorithm to achieve that. So as you notice, I added these two parameters to the function to give the range that specifies the subproblem we are working on. So if we are looking at one element, we return true only if those if AI is not equal to that element. Otherwise, we return false. If we have more than one element in the range from L to R, we divide it into two. So we compute M to be in the middle, exactly in the middle between L and R. And we solve recursively and in parallel the left subproblem from L to M and the right subproblem from M plus 1 to R. We synchronize at this point so that both C1 and C2 are computed. And we return true only if both of these are true. So that's the algorithm. It's obvious that it does the same thing as the previous algorithm, but now it has some parallelism. So first of all, we want to look at the work. We can see that we have not changed the worst case running time of this whole algorithm. If we look at it as a sequential algorithm, specifically the work of this recursive algorithm is quite clearly linear in terms of the size of the problem. So the work can be described by this recurrence. We solve two subproblems of the size half of the original, and then we do some constant work. So this means that work is linear. So the same as the loop that we had here. So the total work for this algorithm will be the same as for the sequential algorithm, n squared. Let's analyze the span of this algorithm. So now we have this procedure check u, which is parallel. The span of it can be expressed with the following recurrence. We are performing in parallel two recursive calls of the same size. So the span is just the span of one of the calls, and then plus some constant span. So that means that the span, when you solve this recurrence, the span is log of n, where n is the difference between L and R. So then what is the total span of this procedure? Well, it can be expressed as just the sum of logarithms of the differences between these two parameters. So the total span would be something like this sum, the sum from I would go from 1 to n minus 1 of log I, and it can be easily shown or seen that this is more than sort of log of n over half. So I throw away half of these, and then I reduce the other half to n, to log of n over half, and that is big theta of n log n, because it's definitely not more than n log n. So we have that the span is n log n, and then the parallelism is work divided by span. This means that it's n over log n, and that is quite good. So for a lot of practical situations, that will probably be enough. We will not have more parallel capability than that. But what if we want to parallelize even further? Specifically, it would be nice to parallelize this for loop, and to make that possible, we want to get rid of this R variable, of this global R variable. So let's just do that. Now, of course, we will not get the result, exactly the result that we want, but maybe we can fix that later. So let's get rid of R, and let's have this B array with these kind of gaps where we, if we see that the element is unique, we insert it in the position I. Otherwise, we say that we assign some special value to that position, indicating that is empty in a sense. So else bi is equal to some special value, let's say infinity. Then this means that now we can safely make this loop parallel. So we say this is a parallel loop, parallel for, and then the only thing we have to add is something here after the loop which compacts B, removing all of these infinities from it. So you can try to stop the video and think and write yourself a pseudocode of that step, and then analyze the resulting parallelism of the algorithm. So here is the algorithm with these modifications. I a little bit compacted the pseudocode for this main loop. Now it's a parallel loop, and there is this one check if it's a unique, the divide and conquer check. Then I assign this element to bi, otherwise I assign infinity. And then I added this sequential part which just compacts array B, skipping the infinite elements and moving all the non-infinite elements to the beginning of the B array. So let's analyze the parallelism of this new algorithm. First, let's look at work. So the work did not change. The work of this is still n squared, because we did not change anything substantial here, and we just added this linear part. So this part dominates. So the work is still n squared. How about the span? First, let's analyze the span of this part. So the span of the parallel for loop is log n plus the span of the one of these iterations, and the span of one iteration is log n plus some constant stuff. So the span of this part is log n plus log n. And then the span of this part is n, because it's just a sequential part. So log n plus n is dominated by n. So the span is plane n. So we have improved the span from n log n to n. And then this means that the parallelism is work divided by span, which in this case is just plane n. So now we have an algorithm with parallelism of n and the span of n. So for all practical purposes, this is enough of parallelization. We can use all n processors. And this demonstrates how sometimes you can achieve higher parallelism by dividing the algorithm into phases, where I factored out this part of compacting the array B into a separate part, so that I can parallelize this other part more. And in this way I achieved a higher parallelism and smaller span. So, but what if we want to push further and see if we can make this even more parallel? So obviously the part to parallelize is this one. How can we parallelize this part? We can do it using a divide and conquer algorithm. It's a little bit more difficult, but you can try to see if you can do the parallelization of this. The trick is to slightly increase work of this part, but drastically reduce the span of it. Try to write a divide and conquer algorithm that achieves this part. Here is a version of the algorithm where I replaced this loop with a call to a recursive procedure called compact, that compacts array B, more specifically compacts the range of the array B starting from index 1 and ending with index n, and it returns the number of elements in that array. So it removes the elements that are equal to infinity and returns the number of elements that are not equal to infinity. So how do we make this a divide and conquer algorithm? Well, just sort of straightforwardly, we first of all look if this is the base case. If the range we have to compact has just one element, so if L is equal to R, then this array is already compacted, and it contains 0 elements if this element is infinity, otherwise it contains 1 element. So that's what we return, and we're done. If this range contains more than 1 element, then we divide the range in 2 equal halves. We call ourselves recursively on the left half, on the right half. We do that in parallel to make this a parallel algorithm, and we get n1 and n2. Then of course we do sync to get the results n1 and n2. And now we have 2 arrays, 2 parts of the array B, one from L to M, another from M plus 1 to R, that are compacted but potentially there is a gap between them, between these two compacted arrays. So we want to shift the array. So the situation is that there is a compacted part of the array of non-infinities here at the beginning. Then there is unused elements, then there is up until m, and then starting from m plus 1, again there is some compacted part, and then some unused elements up to r. Now, to combine these two solutions, we need just to move this part over here. Okay, so that's what we do. This part has size n2. So we just have an array that copies these elements over here. So I just compute the index where to move L plus n1, the size of this, plus the loop variable, and that here gets an element from m plus 1 plus I, which is the loop variable. We do this moving. And we return the sum of n1 and n2. That's the number of elements in the compacted array. Okay, so this seems to be a correct algorithm. Let's analyze the work and the span of the whole algorithm. So, okay, what is the work of this algorithm? We can express the work by simple recurrence. Okay, so the work of this compact part is equal twice the work of half of the problem plus this linear part. And this is a famous recurrence that solves to n log n. So unfortunately, what we did was we increased the work. Remember, that part was just linear, big theta of n. We increased it to n log n. Well, thankfully, we still have this part in terms of work dominating this part, because that part is n squared, if we remember. So still the total work of the algorithm does not change. It's big theta of n squared. So what is the span of this? Well, the span can be expressed through, again, a recurrence. We solve in parallel two subproblems of half the size, and then we do the sequential part, which is linear. So that solves into just plain big theta of n that dominates. So n plus n half plus n fourth plus n eighth. That sums up at most to 2n in the limit, so that's just big theta of n. So we did all that work, and unfortunately we have not improved the span. So remember, the span of that sequential part was just plain n. So far we have not achieved anything. We made the work worse, and we have the same span. So we have not achieved anything. In order to make this useful, we need to parallelize also this loop. Now, can we just write parallel here in front of the for loop? You can try to stop the video and try to think whether we can write a parallel for in front of the for here. And if not, why we can't do that? We cannot write parallel in front of this for loop because iterations of this loop read and write from the same elements. It's quite clear to see, for example, let's say if the gap here was only just one element between these two parts. This means that we have to shift all elements just by one position. And so this means that when we do this in parallel, if we write parallel in front of this for loop, we read and write into the same positions. So we have race conditions and unpredictable results. So we cannot write parallel here. But we can do a simple trick by having a temporary array here, and instead of writing, doing like this, we first write these elements to the temporary array. So we have a temporary array. So first we copy elements to the temporary array, and then we copy, once we have done with that, we can do that in parallel. After that, we can copy these elements into the required positions back in the original array, again in parallel. So again, the same lesson. We cannot parallelize this. We break down it, maybe seemingly artificially, into two phases where each phase can be parallelized. We copy to some temporary array, let's call it T, and we copy from that T back. So let's see how that looks and what is the analysis of it. So let's analyze the parallelism of this algorithm. So first of all, the work of the whole thing did not change. We did not change anything in terms of work. We just split out a little bit this into two. So this is, instead of n, that's 2 times n. That does not change anything asymptotically. So the work is still the same for the whole algorithm, and squared. How about the span? So let's look at the span of this. Now we parallelized this combined step. So this combined step is now not n, but log n. Then this turns out into a simple series like so. It's log n plus log n over 2 plus log n over 4 and so on, and that can be written as a this kind of series log n minus 1. If we assume the log of base 2, we change this this ratio into this difference. 4 becomes log n minus 2, and so on. And that solves to just a simple arithmetic series from log n to 1 eventually. So that solves to log squared over n. So the span of this part is log squared over n. Remember that the span of that was log n plus log n, so that's log n. So this part in terms of span dominates, so that's log squared over n. And so the parallelism is n squared over log squared of n. So we see how we, by steps of breaking down the problem into phases, making these phases divide and conquer, taking care to introduce as much as possible parallelism into different parts of the algorithm, we increased the parallelism from n over log n to n squared over log squared n, which is a big improvement. And in particular, the span was increased from n log n. It was decreased from n log n to just log squared n. So you can ask, okay, but can we maybe even further parallelize this compact. In particular, maybe we can reduce the work of it. And this may be even useful or needed in some situations. So for example, if array A is sorted, then this check just becomes check of the element ahead of AI. So you just compare AI with AI plus 1. If they are not equal, then that means that AI is unique. So this means that this whole loop then has the work of just big theta of n and the span of log n. Then our implementation of compact dominates in terms of work, this part, because it has work n times log n, if we remember. So then it really would be nice to bring down the work of this divide and conquer algorithm to just big theta of n, and actually it is possible to do that, to bring down the work to big theta of n, and also to bring down the span to log of n. That is possible to do with some clever and advanced techniques, in particular some ideas from parallel computation of so-called prefix sums of an array. You can, if you want, you can try to check assignment 27-4 in the Corman et al. Textbook that we use. You can get some ideas from there to further improve this compact procedure.